Hello everyone, welcome back to Math 110. Today's lesson 1.7. We're going to go through some things with some exponents and learn how to handle exponents, represent things in scientific notation, and I'll show you a couple of ways we can handle that. So lesson 1.7, here's our prep skills, understanding and evaluating powers of 10. So frequently we have to deal with very large numbers and very small numbers. When we do that, we don't want to write out just a very long string of numbers, and we're usually only interested in the leading digits and then some power times some power of 10 to give us an idea of the size plus the important digits. So when 10 is raised to a positive power, the result is always 1 followed by a number of zeros. If it was just 0, which is not considered positive, it's not considered positive or negative. But if we raise 10 to the 0, that's basically 1. We've divided 10 divided by 10. If we use our exponent rules, we subtract exponents. So it'd be 1 minus 1. It just gives you 1, right? 10 divided by 10. And that's so 10 to the 0th power is defined as 1. And then the other ones, if it's a positive power, it's always just a 1 followed by a number of zeros. So if I had 10 to the 7th, that's really 1 times 10 to the 7th. So each time I move over, I'm just going to count from 1 point. I'm just going to add 7 zeros. So 1, 2, 3, 4, 5, 6, 7. Exponent is 7. I need 7 zeros. When 10 is raised to a negative power, the result is always a number less than 1. The decimal form begins with the number of zeros and ends with 1. So the number of zeros is 1 less than the size. So again, if I have 10 to the negative 1, that's 1/10, so that would be 0.1. So I would need to move it from 1 to 0.1. That would be 10 to the negative 1. And if I've got negative 4, negative 1, 2, 3, negative 4. So just kind of remember that negative 1 gives me to the 0.1. And then I start moving over from there. So this we've looked at before, writing repeated multiplication as an exponent. If I'm doing 12, 12, 12, 12, 12, that's just 12 to the 5th, 1, 2, 3, 4, 5. That's just that representative of the number. That's what that means, is I'm multiplying 12 by itself 5 times. Same thing for a negative exponent. I'm basically dividing that number that many times. So here, I'm saying 3 to the negative 4th is really 1 divided by 3 times 3 times 3 times 3. 3 to the 4th in the bottom, 1 divided by 3 to the 4th. To multiply two expressions, if they have the same base, these are called the base numbers, and these are the exponents. If this is the same bases are the same, then all I need to do is add the exponents. Bases are the same, 12 and 12, just add the exponent. This means 12 times 12 times 12. I've got 6 of these, 12 times 12 times 12, 6 times. Now all I've got is 6 plus 7, 8, 9 of those. So that's 12 times itself 9 times. So here's the rule that if we divide exponential expressions, we're just going to, the bases are the same, we're just going to subtract the bottom exponent from the top exponent. So here I've got an 8 and a 2. I'm just going to go 8 minus 2 gives me 6. Now what am I doing here? If I expand this out as multiplication, up here I've got 8 of these 7s multiplied together. Down here is the 2 7s, 7 times 7. If I cancel, I've only got 6 of them left. So that's basically a shorthand way of canceling. We're going to look at a little bit of handling, just things like the national debt, small numbers, exponents from growth factors, and things like that. So if you track, let me move this down here so we can read it for a second. If you track the national debt over the last 90 years or so, it can be modeled fairly accurately by the type of exponential growth we studied in lesson 1.4. On average, the debt has grown by about 7.9% per year. So each year we're multiplying the previous number by 1.079. Remember that decimal number, 1, 2, 2 to the left, plus the 1 from the previous year. So it's grown to 1.079 times that. If that trend continues by 2050, it would be 276, 205, 000000000, and by 2100 it would be 12, 300, 00000000000. And if you're like most people, including me, you have no idea what those numbers actually mean. That's pretty large numbers. So I didn't even want to call them out. They're just too big to get any perspective on them other than that's some pretty big numbers. To make it easier to understand and work with numbers of large sizes, we're going to use this idea of exponents and powers of 10 to represent these numbers, and it'll give us a better idea and a way to express them. Okay. So consider the number 300. This is really 3 times 100, right? We've counted 100, 200, 300. So 3 times 100. I'm going to represent that 100 as that 10 squared. 1 times 10 to the 2. That's those two zeros. And that's just an easier way to represent that number. 3 times 10 squared. And I prefer, once we've gone over to that, I keep it as exponents. 3 times 10 to the second. 10 to the 1th is 10. 10 squared is 100. 10 cubed is 1,000. 10 to the 4th is 10,000. 10 to the 5th is 100,000. And that's how we're going to basically express things from there. Okay. Each extra power 10 adds another 0. And if I divide, I reduce the 0. So if I divide by 10, I've actually reduced the 0 that's going to be out there. Okay. So let's look at some of these debt numbers. In 1930, let me move this up here. In 1930, the national debt was about 16 billion. 1.6 times 10 to the 10th. That was in 1930. In 1985, it was 1.823 times 10 to the 12th. That's $1.823 trillion. Okay. So here's the way we can do this in scientific notation. 1.6 times 10 to the 10th. 1.823 times 10 to the 12th. Okay. And because the first part of a number in proper scientific notation is always a number between 0 and 10, you can easily compare the sizes of number by looking at just the size of the exponents. So this is always going to be between between the 0 and the 1 is typically, or the 0 and the 10. And then we're going to express this as a power of 10. I'm going to go from there. Okay. So here's some comparisons. Again, when we're using, this is only comes into play when we're using really big numbers and really small numbers. So Earth is about 2.57 times 10 to the 7th miles from Venus, and about 4.6 times 10 to the 9 miles from Pluto. About how many times further away is Pluto? So if I divided the 2.57, the 4.67 times 10 to the 9th, and if I divide that by the smaller, the 2.57 times 10 to the 7th, if I'm just looking at the exponents, this is, and if I kind of round these things off, pretty much, this is 4.67 divided by the 2.5. They say that's pretty close to 2. You could get a little more accurate with this if you do this on your calculator. But then we're going to divide the 10 to the 9th divided by the 10 to the 7th. At 10 to the 9th minus the 7, it's going to give me 10 squared. That's the 10 to the second. So that is about 200 times as far that Pluto is away further than Venus. So let's do some skill work of actually converting numbers to scientific notation. So I've got this number. When I write a decimal point at the end of the number, so whatever this is, I'm going to start. This is where the decimal point is naturally. We just don't write it. And then I'm going to go from there and I'm going to count it over. So here's the little marks. 1, 2, 3, 4, 5, 6. So that's the 10 to the 6 zeros, and then that's my base right there. Okay. So write each number in scientific notation. I've got this number. I'm going to start here. Here's my decimal place. I'm going to move it over. 1, 2, 3, 4, 5, 6, 7, 8. And then I'm going to put the decimal place here and then keep everything that looks significant. So I want to keep all of these digits here that are non-zero, and then all the ones that have to do with 0 I'm going to truncate out and use that for that. Okay. So the distance in miles from Earth to the Moon is 238,900 miles. I want to represent it in scientific notation. My decimal point is naturally there, and then I'm going to move it over 1, 2, 3, 4, 5. I want to keep my significant digits 2.389, and then I had moved it over 5 places, so it's times 10 to the 5th. For very small numbers, we're going to have to deal with negative exponents. So in negative exponents, 10 to the negative 1, that's just basically the 1 over 10. So this is really 10 to the 0. You remember I told you before, 10 to the 0, that's 10 to the 1. So 0 minus 1 is that negative 1. Okay. So 1/10, that's 0.1, is basically what we know 1/10 is the 0.1. So this 10 to the negative 1 is 1 times 10 to the negative 1. I'm going to move 1 place to the left to represent that, and then I just pick it up from there. I write my 1. I got 10 to the negative 2, so I'm going to go 10 to the negative 1, 10 to the negative 2. That's 0.01 is what that equivalent is. Same thing for 10 to the negative 3, 1, 2, 3. And 10 to the negative 4 is 1, 2, 3, 4. So that's converting those powers over to its decimals. So now what if we start with these decimals? I got some small numbers, and I want to represent those small numbers in scientific notation. So here in this example, I've got 0.000437. Here's my decimal place, and every time I move it over to the right, I'm going to increase the power. So this is times 10 to the 0 by itself. I can go ahead and write that as scientific notation as times 10 to the 0. And every time I do this, I move it over to the right, I really need to replace that I'm dividing it by 10. So I'm dividing it by 10, 1 time, 2 times, 3 times, 4 times. If I put it there, there's my 4 times. So I'm really dividing this number by 10 to the 4th, or 10,000. Okay. So here a typical flu virus measures between, this is 0.000000008 and 0.000000012 meters in length. And I want to represent those in scientific notation. So here's the markings for getting it over 1, 2, 3, 4, 5, 6, 7, 8 to get it in standard position. There's 10 to the negative 8, and this one I'm going to go over 1, 2, 3, 4, 5, 6, 7, and that's my 10 to the negative 7, and I've got 1.2. I want to get it between the first significant digit of that's something other than 0. I want that decimal place to be 1 place past that to get it between the 0 and the 10 mark. So E. coli is a common bacterium that can cause intestinal issues. A typical specimen is about 0.000007 meters long. That would be in scientific notation 1, 2, 3, 4, 5, 6, 7 times 10 to the negative 6 meters. And if I wanted to compare these things, I would kind of divide them out. Based on the size of the exponents in scientific notation, which is bigger, a small flu virus or a typical E. coli sample. This is smaller. The larger negative number is actually a smaller. So this is smaller than that one. So we're going to take this, divide it by that. So I'm going to go 7/8, pretty close to 1. 10 to the negative 6 divided by my 10 to the negative 8. So my exponents, I want to subtract the exponents. Negative 6 minus the minus 8, and that's negative 6 plus 8, which gives me 10 to the 2. So let me do that for you again. Let's see. If I go over here, and I'm going to write 7 times 10 to the negative 6 divided by 8 times 10 to the negative 8. So this piece of it is pretty close to 1. So I'm going to write this as 1 times 10. This is where I'm going to do my exponent work. So when I'm doing exponents division, it's always the top minus the bottom. So this is going to be negative 6 minus, here's my parentheses. What am I subtracting? It's negative 8. 1 times 10 to the negative 6. Negative and a negative is a positive. So that's my plus 8. Negative 6 plus 8 is 2. So 1 times 10 squared would be just simply written as 10 squared. So that's how you're handling that. I just thought I would kind of work that out for you. So here's some things that you can work on converting each number to scientific notation. I would think that's 1, 2, 3, 9.8 times 10 to the negative third. 1, 2, 3, 1.478 times 10 to the plus third. 3, 4, 5, 6, 7. 5.4302 times 10 to the 7th. 1, 2, 3, 4, 5, 6. 5.8 times 10 to the negative 6. Move it back up here. So here's another one. If I'm written in scientific notation, I'm going to take the 4.01, I'm going to move that over, and I'm going to continue to move it and add zeros as necessary. So the 1, 2, 3, 4, 5, 6, 7, 8. I'm going to add those extra zeros. So that would be 3.2 times 10 to the negative fifth. Here's the 3.2. I'm going to move it this way each time, counting back by a negative 1, 2, 3, 4, 5, and adding zeros as I need them. So here's again, this is the number of red blood cells per microliter of blood in an average healthy man, 5.4 times 10 to the 6. We're going to write this out, 5.4. We're going to start with what we have and then add 6 places to the right. 1, adding zeros as needed, 2, 3, 4, 5, 6. So then I just rewrite it, marking off my every 3 just to keep us up in powers of 10 to the third. 5,400,000 cells. The mass of an average human ovum, 3.6 times 10 to the negative 9th kilograms, a mass. So I'm going to start with a 3.6, and now I'm going negative way, so this is smaller. So I'm going to go count 9 times to the left. 1, 2, 3, 5, 6, 7, 8, 9, inserting zeros where there were none, just to get everything back, and that's the size in kilograms as a decimal. Okay, here's some extra practice for you. When a number written in scientific notation has a positive number, a positive exponent of 10, what can we say about the number itself? We say that it's 10 or larger. So if it was 10 to the 0, that would be 1, but it's not considered a positive exponent. So we start with 1, that's 10, and then if we go 2, 3, 4, that's a positive exponent. It's got to be bigger than 10, 100,000. The number between 0 and 1 is written in scientific notation. What can we say about the exponent on 10? That it's going to be negative. So if I had 0.5, I would move that decimal place over. 5 times 10 to the negative 1 in scientific notation. Okay. So if a number in scientific notation has a negative exponent on 10, to convert to decimal form, move the decimal place left because the number is less than 1. So if you use your calculator or even in Excel, if we start getting into very large numbers, they convert to a scientific notation and they use the letter E, capital E, to represent that. So here's some stuff on the calculator. They've done some very large multiplication and it switches the answer into scientific notation, but they use this E as the exponent number, 1.2375 e to the 11th. That's basically 1.2375 times 10 to the 11th. Okay? And you would have to recognize that E. It's not an error. It is the exponent for scientific notation. Here is a picture of the Excel, and they give you that. So this is a large number entered into cell, and Excel has converted it over to 1.24 e to the 11. And then everything here is a e to this. So this one would be 1.24 times 10 to the 11th, 3.20 times 10 to the negative 8. Here is in the calculator 7.44 e third, 7.44 times 10 to the third. You just rewrite E3 as 10 to the third, and then you do our regular conversions. 1, 2, add a 0, and that gets it into standard form. If you need to enter this stuff in Excel, you can do it on your calculator. You'll have like an EE that you have to access to type it into the exponent. You can also go times 10, do an exponent operation, and actually type that exponent in. In Excel, you go over here, here's the different formats of numbers, put it into scientific notation, and I'm going to go 3.45 times, and I'm just going to enter this as, 3.45 e to the 24th, and it will convert that over to that e plus 24. That means positive exponent. And if I do 2.67 e to the 12th, it converts, and now I'm going to do the division. In Excel, I'm just going to reference the cells that it's in and let it do the operations for me. So take what's in A1 divided by what's in A2, and it gives me the answer back in this. E to the 24th divided by e to the 12th, 24 minus 12 gives me that 12, and 3.45 divided by 2.67, you're looking at 1.29. So that's basically that in scientific notation. So that's how Excel handles it, and like I said, the calculator will look some of it in class. So when we're using these exponents, there's certain names that'll keep coming up that we can kind of use. Here's a name that we're going to use for this particular number, and here's the corresponding powers of 10. So if you see 10 squared, you're automatically going to think, well, that's 100. 10 cubed is pretty easy, that's 1,000. And now we're going to go by thirds. Every 3 zeros, remember when we did work commas, since way back in grade school, every 3 zeros we marked them off. This would be the thousands. The next would be the million, so that's times 10 to the 6. So if something was 3 million, you would say 3 times 10 to the 6. If it was in $2.7 billion, we would go 2.7 times 10 to the 9th. 10 to the 9th is a billion. $36 trillion, 36 times 10 to the 12th for the trillions. And we can also go back and forth from there. So if we have a 10 to the 12th, we could just call that a trillion, 10 to the 9th a billion, 10 to the 6th million, and all the way through. So here's a nice table that we should fill in. I'm giving it to you here. And this was the national debt in dollars for the different years, 1930, 40, 50, 60, 70. As it went through, here's what the national debt was here. It was 1.6 e to the 10th in scientific notation. We would like to pronounce it, so we would like to convert this over, but that's 10 to the 10th. But what we're going to do is make that into one of the ones that we know. So I'm going to convert that to 10 e to the 9th by moving that over one time. So 16 times 10 to the 9th. The 10 to the 9th I'm going to call billion. Same thing here. I'm actually e to the 10th or 10 to the 10th. Moving it over, 51 times 10 to the 9th or 51 billion. That's the same thing here, but they're going to move it over 2 places to get it to the 9th. So that's 257 billion, 286 billion, 371 billion, 908 billion. And now we get to 12, that's the trillion. So here would be the 3.233 trillion, 5.674 trillion. Now this is the 13th, so I need to move that over one time. 13.562 trillion, 18.151 trillion. This is what the national debt, the graph looks like. As you can see, there's some exponential properties in it. This thing has really exploded over the years. Okay. Population of the United States was roughly 1.23 times 10 to the 8th in 1930. 3.2 times 10 to the 8th in 2015. If the national debt were to be paid off by dividing the total amount evenly among all citizens, how much would each have owed in 1930? So we had 1.6 times 10 to the 10th in 1930. And we had 1.23 times 10 to the 8 population, people. So this would be, if we divide this out, 10 to the 10th, 10 minus 8 is the squared. This would be about 130 per person. In 2015, this has grown to 1.8151 times 10 to the 13. That's what this is up here. And divided by 3.2 times 10 to the 8 people. And once we do this calculation, either Excel calculator times 10 to the 13th, this times 10 to the 8th, that's going to divide out. You're going to have approximately 5 zeros, 1, 2, 3, 4, and this is a little larger, so that would have been like the 0.56. So $56,722 per person is what each one of us contributes to the national debt. Okay, so that pretty much takes care of this lesson. I hope you found it informative. See you back next time. Have a good day.